So, dear students, today we start the theory part of work-power energy. Second part. First part we have already done. In the second part, the first item is spring. Some natures of spring is in your syllabus. You know, all of you know how a spring looks like. The spring. If you compress it, apply some force, its length will reduce. You can also stretch it by applying some opposite, its length will increase. Now, let us study a few issues about a spring. First thing you remember, there is a term called spring constant. Spring constant is the force you require to deform the spring. That means either stretch it or compress it by unit length, that is 1 meter, when the spring was in neutral condition. That is very important. Normally, we forget that issue. Spring constant K is when the spring was in neutral condition. Because we shall see now, if you already press a spring, then the force required for unit deformation is different. So in neutral condition, if you deform it by unit length, then the force required is K. Remember this. Suppose the spring is compressed or stretched. Both figures are shown here. Compressed or stretched by a small length del x. Why this term small length? It is because you will later on learn in the chapter of elasticity that these theories and this formula, they work when the deformation is small in comparison to the natural shape and size. Then only this formula will work. So we first start with, say it is deformed by a small length del x. Then spring was neutral. In neutral condition, how much force you have to apply per unit deformation is K, and you have deformed it by the amount del x. So how much force did you apply? You applied a force of K multiplied by del x. Here, then comes the second important issue. According to Hooke's law, Hooke is a scientist. You will learn more about Hooke's law in elasticity. That to further deform it by another del x, the force required will be already the first time force that was required K del x, that multiplied by another del x. That means, I repeat once again, very important issue. If the spring is neutral, then spring constant is K. If spring is already deformed by amount del x, then the new spring constant is K del x. Right? If the spring is once again deformed by another amount of del x, then the new spring constant is K del x into del x. This is Hooke's law. Fine? That means the force exerted on the spring or by the spring, right? If you exert a force on the spring, it will be compressed, but the spring also will apply opposite force, which is called elastic force. So force applied on the spring or by the spring is a function of deformation itself. That means how much it is already deformed. You can try it at your home. You take a very strong spring, or maybe you take a, if you get somewhere, is a shock absorber of a car or a motorbike. When you first press the shock absorber by, say, 1 inch, you need certain amount of force. But if you want to press further, you need more force. If you want to press further, you need more force. That means as you keep on deforming, more and more force is required. Such cases you have seen in your basic mathematics chapter. You have to take help of the concept of differential calculus. In order to, if you want to find out that if you press a shock absorber or a spring by a reasonable amount of compression, suppose quite large amount of compression as you desire, then if you want to find out the total force or total work done, you need to take help of differential calculus. So let's see how we do it. Say the spring is already compressed by a very little amount x. And that is where we start our experiment. It is already compressed by a little amount x. Then the force required is kx. Force required is kx. This is our initial condition. Then you further deform it by another amount dx. Then during this deformation, your work done is the force required kx multiplied by the displacement dx. Because we have seen W equal to Fs force into displacement. If it is already defined by x, then the further force required is kx. And then if you deform it by another very small amount dx, then the work done during this small compression is kx dx. So now if the spring's initial deformation was x1 and final deformation is x2, suppose you are given a problem sum, there is a spring with spring constant such and such. The spring is already deformed by, say, 5 millimeter. It is then deformed by another 50 millimeter. What is the total work done? That means initial deformation, starting deformation is x1, final deformation is x2. Then what is the work done? Is integration of this function kx dx. So work done is integration of kx dx from x1 to x2. K is a constant, comes outside the bracket. Integration of x is x square by 2, limit x1 to x2. That is half of k x2 square minus half of k x1 square. This is the equation that you have to remember, that if the initial deformation was x1 and final deformation is x2, then this is the total work done. But say initially the spring was neutral. That means x1 was 0. Then the work done will be half kx square. Initially it was neutral and then deformed by x. Then it is work done is half kx square. You know, this formula is very equivalent, easy to remember. It is like a kinematics equation formula, half mv square. So it is half kx square is the work done if you compress a spring or stretch a spring from neutral condition to a limit displacement of x. Next we go to the word energy. The word energy is very common to all of you. You say, my such and such friend is very energetic, but my such and such friend is very lethargic. So we know what is energy. Energy in our physical day-to-day world, it gives an idea of, you know, how much, uh, how much ability to work your friend has. He works or not, that is different thing, but his ability to work, something like that. So work is done at the expense of energy. In our physics world, whenever you do some work, suppose you push a table or do any some such work, then you have to spend some energy from your body. So work is done in expense of energy. If you have no energy in your body, suppose you are a dead person, then you cannot do any work. So work is equivalent to work. In physics, work is in general, work in general is equivalent to energy. And their units are also same. Both units are joule, but notation, normally we write W for work, and for energy we write either capital E or capital U, something like that. Any different books, there are different symbols used. So work normally is equivalent to energy. Suppose you have a numerical problem where you find out the work done by a person is 100 joule. And then second question is how much energy did he spend? Answer is 100 joule. This is equivalence is considered all that energy he has spent has been converted to work, which of course is not the fact in our real life. This is not in your syllabus, neither in your textbook, but I just give you the hint so that when you go for higher studies in college, you will remember this. Though, in fact, energy spent by a person is little more than the work done by him. It's like that. Suppose you work on something and your work calculated is 10 joule, then your biological body has to spend energy a little more than 10 joule, maybe 12 joule or 11 joule. Why? That is because some work is being done inside your body also. And for that, you need some amount of energy. And that is why there is a term which is called efficiency, which is called work done by energy spent. Suppose you uh, do you do 10 joule work and you spend 12 joule energy from your human body, then your efficiency is 10 upon 12. This term efficiency, you will later on, you will come in your higher studies, maybe in your school syllabus. I'm not very sure at this moment. This efficiency. And when you want to buy some, say, gadgets, suppose a freeze or suppose a water pump, its nameplate, you will always find there is a term called efficiency. Suppose you buy a water pump, right? The water pump does some work to lift water from your underground reservoir to your overhead tank. For this, this water pump has to do some work. Work is equal to mass of the water into G multiplied by height of the water tank from the reservoir, mgh, right? Now say this calculation shows the work done by the pump is 100 joule. And if you look at the electricity meter, you will possibly find that the pump has already consumed 110 joule because the pump needs this additional 10 joule just to run itself. And then efficiency of the pump is called 100 divided by 110. That is called efficiency. Also, I give you the information for your future daily life. Efficiency of various machines are, if its efficiency is 80%, you should consider it is very good. Maybe your motorbike, if your motorbike efficiency is 80, 85%, it's a very good engine. Okay? Okay, that's apart. Next, go to the next issue. This mechanical energy. There are various forms of energy. You have already learned electrical energy, magnetic energy, solar energy, light energy, heat energy, etc., etc. But at this moment, we are in the chapter of mechanical energy. Mechanical energy can be divided into two segments. One is potential energy and another is kinetic energy. What is potential energy? This is the energy possessed by a body due to its position in a force field or due to its deformation. A position in a force field. A glaring example, gravitational field. Anything around the earth is under the gravitational force field. And here, anything you lift from bottom to, from lower level to higher level, some work has to be done. Now, if you lift something from lower level to higher level, you have to do some work on the body. And that amount of work, that many joule, is stored in that body itself as a potential energy, or by say deformation. Same thing of the spring. If you compress a spring, you work on the spring, right? But if you let the spring release, then the spring will push you back. That means spring will work on you. And when the spring worked on you, what did it get the energy? It got the energy first time when you worked on the spring. So spring stored that energy as a potential energy. Or the body or the mass or a block which you have lifted and kept in the first floor or on the top, on the branch of a tree, it stores that potential energy. And if you let that block fall on your head, you will see that the block works spending some energy, right? So this is potential energy. Suppose a block of mass M is lifted by H unit against the gravitational force like this. Suppose it is lifted. Then how much force required to lift the block was mg and the displacement was h. So what was the work done? mgh. Potential energy of the body is mgh. This work done, or this many joule, is stored in the body as its potential energy. And when time comes, it will use that energy. Like if you let that body fall on the ground, and if you are standing there, that body will fall on your head and maybe kill you or murder you, and using that energy which is stored in it. On the other hand, kinetic energy. Kinetic energy is the energy possessed by a body due to its motion. Like if you fire a bullet, then the bullet had some energy to kill somebody. How it gets that energy? Due to its motion, due to its velocity. Suppose a force is applied on a block of mass m at rest so that its velocity is v after a displacement of s, like this. So after a displacement of s, its velocity v. Then we know from the kinematic equation, v square equal to 0 square plus 2as. A is the acceleration. So acceleration of the block is v square by 2s. So if you know the acceleration, what was the force applied on the block is mass multiplied by its acceleration is mv square by s. This was the force applied on the block. And what was the work done on the block is this force multiplied by displacement. That is mv square by 2. That means kinetic energy of the body is mv square by 2. So this is these two formula you should remember. The potential energy in gravitational field mgh and kinetic energy is mv square by 2, right? Now we go to another term which is called power. This term is used in our daily life in a very, yeah, in many ways. Suppose we say, oh, such and such police sergeant is very powerful. Very powerful. Normally in our daily lives, we say means that guy is very cruel. He can kill or murder anybody anytime, or he has many big shots, higher officers under him. So this is called powerful. Another powerful is, suppose I say my friend Rama is very powerful. Then I mean to say Rama has got enormous ability to work. He has got enormous energy first, then not only energy, he has the ability to spend or use that energy. So power is the rate at which one can work or one can use his energy. So mind it, having energy full, having your body or your belly full of energy is not powerful. Have energy, small or big, little or large, but you have a physical ability to use this power in a very quick way, very fast. That's called power. Like this. Say Rama pushes the box by 1 meter in 4 seconds, like this. This is Rama. And say Shama. You have seen the Shama is little healthier than Rama. Rama is thin, but Shama is healthier. And Shama pushes the same box, same 1 meter, but very fast. And we call Shama is most powerful because he can do work in a much faster rate. So Shama does the same work in less time. Hence we call Shama has more power. Similarly, in your motorbike or in your domestic water pump or any machine you use, when you talk about power, it means it has the ability to work in much faster time, ability to work much faster. Then it is called more powerful. And so power is definitely work divided by time. So if you have a numerical problem that the water pump does such and such work and etc., find out its power. You have to calculate how much work it has done and then find out how much time it has taken, and their ratio is the power of the body, right? So that is all in this chapter. Next time, we shall see the numerical problem.